Okay, picture this, an earthquake, but so incredibly powerful that it doesn't just shake a planet, it actually fractures the surface of a dead star. We're talking about a cosmic event that unleashes more energy in a tenth of a second than our sun will in over 100,000 years. And believe it or not, this isn't science fiction, it's a very real thing called a starquake, and we're about to figure out exactly what it is.
So our story really kicks off on a specific date, December 27th, 2004. On that day, something totally unexpected and, frankly, a little terrifying hit our planet from the absolute depths of space.
Out of nowhere, this wave of energy just washes over the Earth, and it physically messes with our upper atmosphere. The blast was so intense, it completely overwhelmed the detectors on every single X-ray satellite we have in orbit, just blinded them. For a moment, this flash from clear across the galaxy was brighter than anything we had ever seen outside our own solar system.
So the question is pretty obvious, right? What in the universe could possibly do that? I mean, what kind of object from 50,000 light-years away, that's on the other side of the Milky Way, could unleash that much power all at once?
Well, the answer is one of the most extreme objects in the entire cosmos. And it's not some giant exploding star. No, it's its tiny dead remnant, the neutron star.
See, neutron stars are basically born from death. They're the collapsed cores left over after a massive star runs out of fuel and just explodes in this huge event we call a supernova. What you're looking at here, this is the Crab Nebula. It's the beautiful mess left behind by one of those explosions. And right there, in the very heart of it, that's our culprit.
Now, to really understand a starquake, you first have to appreciate just how bizarre these things are. For starters, they are unbelievably small. A typical neutron star is only about 20 kilometers, or maybe 15 miles across. That's about the size of a city.
But here's where it gets crazy. Crammed into that city-sized ball is the mass of about 1.5 of our suns. All the atoms have been crushed so violently that the protons and electrons are forced together to become neutrons, packed side by side.
The result is a density that your brain can barely handle. A single teaspoon, just a spoonful of this stuff, would weigh about 1 billion tons here on Earth. The only thing in the universe denser than this is a black hole. That's it.
And because they're formed from the collapse of a much bigger spinning star, the rotation just goes into overdrive. You know, think of an ice skater pulling in their arms to spin faster. It's like that, but on a cosmic scale. Some of these things spin hundreds of times every single second. That's faster than the blades on your kitchen blender.
So, let's recap. You've got this tiny, super heavy, insanely dense, rapidly spinning object. What happens when something that extreme breaks? Well, that's what a starquake is all about.
Neutron stars actually have a solid outer crust. But when I say solid, that's a huge understatement. Computer models suggest this crust could be up to 10 billion times stronger than steel. It's very possibly the strongest material in the entire universe.
A starquake is what happens when the enormous stress on that crust just becomes too much. It's just like tectonic plates shifting here on Earth causing an earthquake. The neutron star's crust suddenly fractures and rearranges itself. We might only be talking about a shift of a few centimeters, but on an object this extreme, the consequences are, well, astronomical.
But to get the most powerful starquakes, the superquakes, you need a special kind of neutron star, a magnetar. Now, a regular neutron star's magnetic field is already trillions of times stronger than Earth's. A magnetar's field is up to 1,000 times stronger than that. It is the most magnetic object we know of, and that colossal magnetic field puts the crust under constant, unimaginable stress, making it the perfect stage for the most violent starquakes in the universe.
And that brings us right back to that incredible event in 2004. Because it turns out the source of that blast, a star called SGR 1806-20, wasn't just any neutron star. Yep. It was a magnetar.
The whole thing unfolded with unbelievable speed. The crust fractured, and within a tenth of a second, the first gamma-ray flash erupted. That initial burst was so powerful it physically hit Earth's ionosphere from 50,000 light-years away. After that, a pulsating tail of X-rays was detected that matched the star's 7.6-second rotation perfectly. There was no doubt where it came from.
Now, to really put the power of this thing into perspective, just look at this number. In that first tenth of a second, the magnetar released more energy than our sun has produced in the last 150,000 years. It's a number so big it's hard to even think about.
And this might be the most mind-bending stat of all. If we tried to measure the energy of that starquake on the same Richter scale we use for earthquakes, it would be a magnitude 32.
Now that scale is logarithmic, so this isn't just a little bigger. It's trillions upon trillions of times more powerful than any earthquake ever recorded on Earth. Just insane.
And here's why this matters to us. That star was way over on the other side of the galaxy, thankfully. But if a magnetar like that were, say, 10 light-years away, which is a close neighbor in cosmic terms, a flare of this size would probably strip away our ozone layer, it would bathe the planet in deadly radiation, and could absolutely trigger a mass extinction event. It's a cosmic shot across the bow.
So these events are clearly powerful, maybe even terrifying, but they're more than just cosmic fireworks. For scientists, they are priceless tools, giving us a unique lab to study the universe.
I mean, let's be real. We could never, ever hope to create the conditions inside a neutron star here on Earth. The gravity, the pressure, it's all just too extreme. But we don't have to. When a starquake happens, nature runs the experiment for us, and it sends us the results in the form of light.
By studying the vibrations from a starquake, it's a science called astroseismology, we can actually map the inside of these objects. It's a lot like how geologists use earthquakes to study Earth's core. We can test Einstein's theory of general relativity in an environment of gravity so strong it almost breaks physics. And, most importantly, by listening to how the star rings like a bell, we can start to figure out the fundamental nature of matter itself.
And this gets us to one of the biggest unanswered questions in all of physics. What is the core of a neutron star actually made of? Is it a superfluid sea of neutrons like we'd expect? Or does the immense pressure crush even the neutrons themselves, creating an even more bizarre state of matter, like a soup of fundamental particles called quarks and gluons? A star with a quark core would ring differently than one with a neutron core, and starquakes are our best shot at hearing that difference.
Starquakes give us this incredible, fleeting glimpse into a world that's completely off-limits to us otherwise. They're a powerful reminder that the universe is an active, violent place, and that even in the death of a star, there are profound secrets just waiting for us to find. The question that's left is, what other secrets are these broken stars waiting to tell us?